So in the unit 2, first data structure is called stack. So already we have informally discussed about what the stack is. The stack basically follows LIFO rules. LIFO. The LIFO stands for last in, first out. Last in, first out. Last in, first out. So LIFO rule. We know because if you stack something, stack of books. So if you are keeping one book over the other, so if you take the first book, you can take the book that is available at the top. So this stack having several applications, and it's a very useful data structure. So that's why even when you learn something about the hardware, you will be knowing about it. That is, the system will be having internal stack. Internal stack already it is implemented. Actually, how it works is similar to what we discussed, the logic what we discussed. At the same time, sometimes what happens is some of our applications that needs this particular concept, the stack concept. So that time we can implement it as an external stack. Our program will do it. So we are trying to study how to write the program for developing the data structure called stack. One application I can say based on what you have studied so far. Probably in the C language, when you study it, you might have used the procedures, right? You might have used the procedures. So maybe when your problem is, when your program is quite big and some portion of the program is going to be executed several times, then obviously we go for procedural concepts, right? You will introduce some procedures and do that. Functions. There is a difference between function and procedure, but for C, anyway, we interchangeably use it. Okay. Generally, the functions will return something, but procedures won't return. But here, the conceptually, see, if you take that, it is having only functions. Okay, no problem. It's only a terminology. If you have studied Pascal, another language called Pascal is there. So there, they classify this into procedure and functions separately. Suppose this is our main program. So main program, some lines of code is there. And here it is calling a function called A. Maybe something else is also there. So once this call comes, the control goes to the function A, right? So function A, once again, some codes are there. Let us assume it is calling another function called B. So now the control goes to B. Therein some lines of code executing. Then after that, it will return to this point. After finishing that, it will come to this point. Then finishing that, it will come to this point like that. So here, system will maintain internal stack. System will maintain internal stack. Why it needs is, for example, if you execute something like that, here some variable declaration, variable assignments, okay, some initialization there. So every variable which you have used having some values, but those values are required when you come here, right? Those values are required when you come here. But now what happens is once you execute this, the control goes to this particular point. So here also some variables there, some statement like that. Then after that, once again, these things are required at this point. Okay, after completing that, when you come back, you should get the detail, right? So once B is completed, you have to get the details about whatever the values you need from that. Also, where you have to return. Okay, after B is completed, we have to say that this is a place you have to return. So this address is also important. Here also this address, that is also important. Therefore, we use a stack. In that stack, we store all the temporary values and return address. So why we are using the stack is because once I make this call, these values and this address will be stored in the stack, right? This I need only at the end. This I need only at the end. Then when you make that, then these values and this return pointer will be there. So once I completed, this is what I need. So I can pop it out. So last in first out. What we entered last, that is required at the first time. So here the stack data structure is required. First we can say the structural definition for the stack. So what we have to say is we have to say structure. Then the name of the structure. Here name of the structure is stack. And what the stack will hold. So it will I mean we insert only the items, right? Item. So this is the name of the structure. So it is something like structure we write in the C program, almost similar only. So we give a structure keyword in the name of the structure. This is user defined. Okay, so as we are dealing with the stack, we are saying the stack, and in the stack, what we do is we insert or delete items. Okay, items. So item can be anything. It can be integer, strings, or any other object, whatever it may be. Okay, so in general, we say that it is an item. So after giving the name, you have to declare the functions that act upon this data structure. So declare. Okay. So here we have to give the functions. So these functions we can perform on the data structure called the stack. Here for the stack, the first function is create. Create. So what this function that will do is it will create an empty stack. It will create an empty stack. Therefore, so if you call the function create, what it returns is a stack. What it returns is a stack. Okay. And another function that is called add. Add. So what we add? We add item. Adding means inserting or pushing. Okay. So we name the function as add. What we are adding is item. Where we are adding? Into the data structure called stack. Okay, sorry. Stack. Okay. Add item, comma stack. So once you have a stack there, if you add item, once again what will be returned is the stack only, right? Stack only. The next one is delete. That is also called a remove or pop out. Pop the element. So delete. Delete. So from where we are deleting? We are deleting from the stack. So after deleting what we have? So we are deleting only the topmost element, right? Even after removing that, so we will be having a stack. The next function is top of stack. That is in the stack, what is there at the topmost position that we are looking at. 1 minute, let me take water and pass. Okay, top of the stack. So the top of the stack, if this function is called, what will be returned? It will return item, right? So item is there. What item that we not know? These are all only the declaration part. And one more thing is isempty. Isempty stack. So this will verify whether the stack is empty or not. Okay. So if it is empty or not means what it returns? It returns boolean. Boolean means yes or no. Answer is yes or no. Only binary, right? So what it returns is boolean. So that means the answer is yes or no. So with this, the declaration part over, only these 5 functions we can execute on the stack. So apart from that, based on these functions, we can derive some axioms. Axioms, any number of axioms we can write. but we'll write it for the examination. You have to write at least 4 or 5. Even if you write 4, that would be sufficient. So based on these functions. So axioms, how we write is, now we say for all S belongs to stack. So that means stack contains set of all stack. Stack means set of all stack. In that S is one of the elements. So S is a stack. So similarly, I belongs to item. So there are several items there. We are saying that I is an item. So S is a stack, I is an item. Then our axioms, some axioms. So axiom is you need not write only this. You can write your own axioms, no problem. Okay, but these functions will be common. These functions you cannot change, but axioms you can change. Okay, the first axiom what we write is summed. Okay, summed stack create. So you see now the axioms are based on the functions. So now you see create means creating an empty stack, right? So here we are checking is empty yes, whether that stack is empty or not. So answer is yes, right? So answer we are writing like that. True. Answer is true. So empty always returns boolean. Boolean means it will be true or false. Now sometimes if you say something like empty stack, then within that if we say add I comma s, then what happens? There is a stack already. There we are adding an item. After adding the item, we are checking whether it is empty or not. Obviously, it will not be empty because this element is added, right? Surely it is not empty. So if it is not empty, then it will return false, right? False. Similarly, we can say delete. Delete within bracket create. Here what happens? Create will create an empty stack. So we are trying to delete from an empty stack. So we cannot delete, right? So nothing is there in the stack. So if nothing is there in the stack, we cannot remove anything. Therefore, when you execute delete on a create function, that will return error. That will return error. Suppose we delete like this, delete, then within that add I comma s. Now what do you get? Add I comma s means in the stack item I is been inserted, right? So it is a last and first out data structure. So item which we inserted last will be there on the top. So whatever the element that is there on the top, that will be removed first. So when you say delete, within bracket add I comma s, I is on the top, so I will be removed. So what do you get? You get value I. Okay, you get? Sorry, no. According to the function, no, it is not I. Okay. So delete, add I comma s. Actually, delete what it returns? Stack, right? It has to return the stack. That is stack after removal of the item. So what we get is we get yes. Okay, the same as we get. The stack name is yes. The yes we will get, right? Okay, now if you say top add I comma yes. So if you give that, here we get because top will return the item. So in this case, it will give I. Okay. So like that, you can write some axioms. So if the question is something like define stack means you have to say that stack is a last and first data structure and is defined as, then you have to write this. Okay. So this is called the structural definition. So for every data structure, there is a structural definition. Because at the very first class, we have seen that data structure can be considered as abstract data type, right? So abstract in the sense that we can know that what it does rather than how it is. So this is what we needed, because once we have such a definition, we know that in this stack we can execute these functions, and if we execute that, what will happen? Okay. Then at the end, in order to define it is the end of that, you can say that end and the name of the structure, that is stack, end stack. Okay, so implementation of stack is not over. Suppose the question is something like define a stack and implement. So implement means you are not going to implement in a system. I am talking about the theoretical exam. Okay, so you have to give the code for such implementation. If it is practical, then according to your programming language, you have to do that. Okay, so there you cannot give something like that. So there will be some variation in the practical implementation, but theoretically you have to give like this. Okay, now the implementation, what we have to say is we have to say how to implement these functions. How to implement these functions. So let us see one by one. First, the function is create. So create will create an empty stack. So my function, that is create. So this is equal to, how I do that is I have to declare an array, right? Declare an array. So array name is stack because my structural name is stack, right? So I am declaring an array called stack, and array is from 1 to n. Okay, this is only a algorithmic language. So we are writing like that. Suppose you are implementing a C language, then what you do, stack within square braces 1 to n, right? Sorry, stack n, size n, right? So that way you can do. So depending on the programming language, it may vary, no problem. Okay, declare. So we are declaring an array. How we are implementing the stack? It is by means of an array, right? So that means we assume that there is an array. This array name is called the stack. Okay. So we are declaring a stack of size n here. So there are the array size is n. Then after that, what we have to say that we have to set the top pointer. We have to set a top pointer because we should know where we have to insert next or where we delete next. So there should be a pointer. Okay, so initially the top pointer, now when you say 1 to n means array index will be 1, 2, 3, etc. up to n. Okay, so now nothing is there on the stack. Still we have to define top pointer. So we say that the top pointer will be 0. Okay, then next time when you are inserting element, after inserting the top pointer will be moved to the, that is top will always point to the topmost element. Okay, this top pointer will always point to the topmost element. And again, initially the stack is empty. Therefore, we say the top pointer is equal to 0. Whenever I use this symbol, this is called assignment. Whenever I use this symbol, this is called return. Return. Actually, this language is algorithmic language, that is called the Sparks. S-P-A-R-K-S. Sparks. There is a language called Spark. So the expansion of this is smart programmers are required to know Sparks. Okay, so short form is Sparks. Expansion is smart programmers are required to know Sparks. Okay, so that particular thing only I am using here. Okay, so top is equal to 0. So now the create function is over. Create function will create an array. 1 minute. Okay, so it will return an array that is empty and set a pointer, the top is equal to 0. Okay, next function, when we add and delete, we can see later. So next one is empty. Let us see how to implement empty. So empty, yes. Okay, so empty of stack, right? So according to this, empty of stack. Empty of stack. Anyway, now our stack name is stack that we know. So empty of stack, that is a declaration. So declaration, we cannot pass this, exact value, right? So when the function is called, we have to give the correct value. So empty stack. So empty stack is, we are trying to detect whether the stack is empty or not. So how will we identify whether stack is empty? Based on the top pointer, right? Based on the top pointer. If the top pointer is 0, stack is empty. Otherwise, stack is not empty, because every time when you insert the element, the top pointer will be moving. So top pointer will always point to the topmost number. For example, 5 elements are being inserted. The top pointer will be 5. So fifth element, it will point to the fifth element. So if the top is equal to 0, it is empty. Therefore, what we have to do is, we have to check the value of the top pointer. So if, top is equal to 0. So this is an assignment, this is comparison. So difference here is, this is assignment, this is comparison. Okay. So if top is equal to 0, then what happens is empty stack, right? So if top is equal to 0, it is true, right? It will return Boolean. It will return Boolean, right? Then we can say that true. Else it will return false. Else it will return false. Okay. Now next function is top. We can see top. So top of stack. Top of stack. So how we implement top of stack? So that is, first we have to check that whether stack is empty or not. So if it is empty, then we cannot take the topmost element, right? So for that checking, we are once again using top pointer. If top is equal to 0, nothing is there in the stack, and hence we cannot determine any, we cannot return any topmost value, right? Therefore, in this case, what it is doing is it will return an error. So otherwise, what it returns is the stack of the top. So whatever element on the topmost position, that will be written. Okay. Then two more functions available. One is called the add function, other one is called the delete function. Okay. Now we can see the algorithm for add function. So we can say add. Actually, add having two parameters. Okay. One is called item, and the other one is called stack. Anyway, we have item, we are not sure about here. So it can change. Therefore, once again, we are putting item, but the stack name already we have defined. So that we are saying item stack. But apart from, declaration part, only two things are there. But apart from this, we need some additional information. So when we are implementing it in the program angle, accordingly we can write, but it's a theoretical one. Therefore, we are passing that value also in order to make the function clear. And one more value, that is n. N is the size of the stack. Because here we have declared the stack 1 to n. So n is the size of the stack. Then after that, we need a topmost pointer, right? Then only we know where we can insert. So there are 4 parameters available: item, stack, number of elements, maximum size of the stack, then topmost pointer, the current pointer value. Okay, so 4 things are there. Here, first we have to verify whether we are able to insert or not. For example, if you have a stack and stack size is equal to n, if whole stack has been filled, all n elements are been inserted, then that means stack is full. Stack is full. If stack is full, you cannot insert a new element, right? So that condition we have to verify. For example, the stack is full, the stack indices are from 1 to n, right? So if the stack is full, the last element we inserted in the nth position, and hence our top pointer will be pointing to n, right? So every time the element is inserted, the top pointer will point to the topmost element. So if top is equal to n, that means stack is full. So that condition we have to verify. Okay. So what we do is, if top equal to n, if top is equal to n, then we have to return some error message. We have to return some error message. For that, we call a function called stack full. We call the function stack full. So this is only a function, something like we say that if this is there in normal C language or say printf. Okay, so we say that the stack is full like that. Here we are saying that we are calling the function will do this, return the message, something like, okay. Else, suppose this condition not satisfied, then what happens? Actually, anyway, here we can assume that this function returns error message and return from the code, return from the code. So that's why we are calling that. So once a return, it cannot go to the next line. Okay. So else part is not required. Anyway, if this condition satisfies automatically, this execute and returns. So we can write the code continuously. So otherwise, what happens is the stack is not full. Therefore, now suppose this is a position where the topmost element available. What we have to do? We have to increment the top that point to the next position. So top is equal to top plus 1. After that, we can insert the value, right? So we can say top is equal to top plus 1. Okay, so in order to accommodate the new element, then after that we have to do stack of top that is equal to item. So item is what we have to insert. Okay, then we can say end of the add function. End of add function. So this is what the process for inserting. So now what happens? Element will be always inserted at the top, not at the middle, or not somewhere. So always the element will be inserted at the top. And the last function, that is the delete function. Delete function also same thing. In a similar way we can do that. Delete. Here also we are giving item. It's a variable. Why we are giving is we have to return the item. We have to return the item, right? So we are returning through the parameter. So that is also possible. Return through the parameter. That's what our assumption here. So delete item. Okay. So don't think that we are deleting this particular item. No. After deleting the topmost element, that value will come to this variable. So that value we will make use of to identify what item we deleted if required. Okay. Item. Then name of the stack. Stack. Then what we want is we want the topmost because maximum number of elements are not required, right? Maximum size is not required. Anyway, we are deleting one by one. So when it is coming to top is equal to 0, there is no element. Otherwise, we can remove. Therefore, top pointer only giving. Okay. Here, like in the add stack we checked for stack fullness. Here, what happens? Sometimes stack will be empty. If it is empty, we cannot delete. If it is empty, we cannot delete. Therefore, the condition is if top is equal to 0, there is a comparison statement. Top is equal to 0, then we call the procedure that is called stack empty. Stack empty. So it will say that stack is empty and return from the procedure. So otherwise, what happens? Already that suppose this is a position where the element, the top pointer points to that. Okay, we have to return the item. We have to delete the item. So after that, the top pointer should come down, right? Because once this item is deleted, the topmost item is this one, right? So the top pointer should be decremented by 1. So first, in order to return the value, what we can say is item is equal to stack the top pointer, stack top. So whatever is there in the stack, that will be returned to this item, and that can be taken into our other codes through this parameter. Then top equal to top minus 1. Okay, then end delete. End delete. Okay. So if the question is something like explain stack, something like that, then you have to say the properties of stack, structural dimension of the stack. Okay. Then implementation of these functions. These are all you have to do that. So if you have the logic, then nothing to memorize. Anyway, based on this diagram, I have explained to you what we are doing. So if you have the logic in your mind, accordingly you can write. Okay. So this is not a very complicated thing. So if you have the logic, you can always write the code straight away. Okay, now we have seen the structural definition and the implementation of the stack. Now let us do the analysis part. So that is important. So for every data structure, we cannot see the details that much. So later on, quickly you can understand the complexity and other things. There are two major operations. So one is this, other one is this. However, in the other functions, like create, is empty top, only one line of state, one comparison, one return, like that, or one assignment. So when you do the algorithm analysis after writing code, that will be of this format. So we have to have in mind that every instruction will take 1 unit of time. What is that 1 unit? We do not know. It may be millisecond or microsecond. Okay, let us not bother about it because it is only a theoretical analysis. So in general, we call one instruction will take 1 unit of time. Therefore, those three functions create, is up to top, only one assignment or one comparison, something like that. We can say within 1 unit of time we can do that. However, when you take the add, there are several things. That is one comparison here. Then if it satisfies, this return will be there. Or one assignment statement. Then one again one assignment statement, like that. So if you take the add function, this is even if you say this 1 unit, this 1 unit, 1 unit. Because either this will be 1 plus 1. Okay. So it may execute or may not execute. We do not know. But this conversion will be carried out. So 1 plus 1 plus 1, 3. Okay. Maximum 3 units of time that is figured. But 3 is a constant. If 3 is a constant, already we know that any constant asymptotically it is order of 1. So and against the add function will take only order of 1 time. Okay. So similarly, even if we take delete, so delete will take order of 1 time, because even if you consider this as 1 unit, 1 unit, only maximum 3 units. So 3 is the constant. So order of 1 time. So all the functions that can be executed in order of 1 time. Earlier we have seen best case, worst case, and average case. If you take a problem and if you design the algorithm for the problem, okay, after that you can see best case, worst case, and all. But in this case everything is same because everything is constant only. So in all cases it is order of 1. Basically these complexities we look at the worst case, because worst case is gives the upper bound. Anyway, after that, whatever the instance we consider that the complexity cannot go beyond the worst case. Okay, that cannot go beyond the worst case. Now there is one more analysis available. Anyway, that is not in the syllabus, but for you to know, I am giving that because you have to think in that angle also. If I write the code for the data structure, I am not going to execute any one of the function. Maybe even if I take a stack data structure, I may call several add functions, several delete functions like this, right? Several elements I have to add. So every time whenever I am adding the element, I have to call the add function. So whenever I am removing the value, I have to call the delete function. Okay. So add function and delete function. Therefore, you see, but the create function we call only once. But other 4 functions you can call any number of times. So normal worst case analysis with the assumption that, okay, we always consider the worst case of every function. And if the function is called for n times worst case complexity of that function. For example, if you are doing a push, if you are calling add, add is taking 1 unit in the worst case, right? So if we call and n times means n into 1. So that is n. So total complexity R of n. So this is what our worst case analysis. But unfortunately, this cannot give a best upper bound. So upper bound means if n is upper bound, n square is also upper bound, right? So we have to have, or we are interested in getting the best upper bound. So once again, another example I can say that you consider integer division and floating point division. You know that system will always take more time for floating point division compared to integer division, right? So theoretically, if you say in the worst case analysis, if you say 1 unit of time for integer division and 1 unit of time for floating point division, and if you do the calculation, then you will get the worst case analysis or worst case value. But practically that is not like that, right? Practically it is not like that. So integer division will take lesser time compared to the floating point division. So if the integer division is doing lesser time, then the extra time, spare time it has no, the extra time that can be utilized for doing the floating point division. Therefore, whenever you are doing the analysis, if you want to have better upper bound, so we have to consider sequence of instructions rather than one instruction basis. Okay. Even the data structure also, that's why I told, when you define a data structure or when you implement a data structure, you may call these functions several times. So sequence of functions calls are there. So in that case, why we look at 1 unit time for each call? If we do that, we may not get the best upper bound. Okay. Therefore, there is a method that is called amortized analysis. Another analysis there that is called amortized analysis. So in the amortized analysis, we consider the sequence of instructions. Okay, just to do amortized analysis, so let me name this function as push function. So this is common term, but anyway, here I have given according to the textbook, I had to delete. So commonly people say push instruction is add and pop instruction that is delete. Push and pop. Push and pop are the two important functions in the stack, because this is what more time after creating and all these two functions, so we have to do that for adding the element and deleting the element. Okay. So in the stack, now I am modifying the stack function. Okay, now I am modifying, already we have seen the functions available in the stack. Now I am adding the function, modifying the function, not all, but only pop. So push and pop are the two instructions we know in the normal stack. Now I am modifying that as we have push, the same as what we consider here. And instead of pop, I am considering multi-pop. So this is only for you to understand how this analysis is to be carried, multi-pop. So push instruction, push X, that is pushing one item into the stack. Multi-pop means S comma K. So S is a stack. So multi-pop means we can pop out more than one element at a time. Here we are popping out only one element, but here we are popping out more than one element. So from the stack, K elements that appear at the top of the stack, top K elements to be removed. So that is what called multi-pop. So with one instruction, we remove more than one element. Now we don't have this, and this stack is called the lazy stack. So we can name that as new name. Okay, new name. It is not like that, because anyway here popping out instead of doing one by one, it's lazy, so it is doing popping out so many things. Because naming is very important. In China and all, people used to say, when a child born, they throw a stone inside the kitchen. Then the stone will hit the utensils and make a ching chong chang. So ching chong chang is their name. So it is not like that. Okay. So lazy stack means because it is doing laziness while doing the copy. Okay, now these two instructions are available. Now we want to execute. We have an application. In our application, we want to execute n instruction, I1, I2, etc. In. There are n instructions available. We do not know what these instructions are. But we are very sure that this instruction will be a push instruction or multi-pop because only these two instructions available, right? It may be some push instruction, something will be multi-pop, or all may be push, or all may be multi-pop. We do not know. Now, we have to see the worst case analysis of this. As far as this is concerned, push instruction, worst case complexity is always order of 1, right? Already we have seen that. But the multi-pop, the complexity is order of minimum of cardinality of S, K. Order of minimum of cardinality of S, K. What is cardinality of S? That is number of elements present in the stack. Because suppose you want to remove 10 elements and the stack is having only 5 elements, you cannot remove 10 elements, right? So if that's the case, whichever is minimum that we are doing, suppose it is having more than 10 elements, we can remove 10 elements. So K is the number of elements that is to be removed, and the cardinality S means number of elements presently available in the stack. So whichever is minimum, that much complex, because removing is not been done at a stretch one by one only, right? Top one, the next top one, like that. So that much time we have to spend, right? So this is the complexity for multiple. Now compared to this and this is larger. This is larger. So if this is larger, at the maximum, how many elements you can pop it out? If the stack size is n, in a single multi-pop, all the n elements can be popped out, right? All the n elements can be popped out. So the worst case complexity of this is order n, right? So that is maximum. Worst case. It may not be, not order of n always, not order of n always, but the worst case, as per our theoretical analysis, we assume that the worst case we can remove all the elements there in the stack. If the stack is full, so order of n time. And compared to this and this is larger. Therefore, when I have a sequence of instructions, okay, when I have sequence of instructions, if all the instructions are multi-pop, then I get the worst case value, right? So all the instructions are multi-pop, I get the worst case value. Therefore, if that's the case, this will take n unit, this will take n unit, this will take n unit. So totally n into n. So that together it will give order of n square time. So n plus n plus n plus like that n times. So that is equal to n square. So this is the complexity of executing these n instructions. But this is not correct. This is what our worst case analysis gives. The upper bound, the worst case analysis gives. But what we are saying is this can be done in order of n time. Altogether, all the instructions that can be done in n time. So there are several methods are available. So commonly used method, one is called accounting method. Accounting method. So accounting method is something like a bank transaction. Suppose you are working in a company and you are getting 10,000 rupees as salary. Anyway, it's less for you, but don't worry, this is only example. You are getting 10,000 rupees per as your salary. So you got the salary for this month. So 10,000 in your hand. And you spend 6,000 rupees for various purpose. Then what will you do with the remaining 4,000? Will you give it to me? You will save it into the bank, right? You will save it in the bank. So now your bank account is having 4,000. So next month again you are getting 10,000 rupees, but your expense is 12,000. So 2,000 extra. How do you manage this 2,000? You take from the bank where you already saved the money, right? So the same thing the system is doing. So here we are talking about a time. Sometimes some instruction that needs lesser time. So some time that can be saved. The saved time will be utilized for executing something else. So this is called accounting method. So when we say this is accounting method, we have to talk in terms of rupees. Then only it is better. So this is for the analysis purpose. So I have two instructions. One is called the push instruction. Other one is called the multi-pop. Multi-pop. So what I have to do is, whenever I want to push an element inside the stack, I will give 2 rupees to the computer. So don't ask how the computer will get 2 rupees under. So we are paying something. It's accounting method. We are paying something. So I want to insert one element inside the stack. I am giving 2 rupees to the computer and telling the system, please take this 2 rupees. Actually, you need 1 rupee for pushing an element. Anyway, balance 1 rupee you there, that you take it. System is very happy because it is getting more than what it is doing. Okay, so system is taking 2 rupees, 1 rupee it is spending for pushing the element, and 1 rupee it is putting in its pockets. Then later on, I am getting the multi-pop. Okay, so multi-pop, I am not paying any rupee, so 0 rupee I am paying. And the system is getting angry. System is telling, hey boy, you have given 0 rupees and asking me to popping out some elements. How do I do that? Then I say to the system, you see, if you have 5 elements with you in the stack, if you have 5 elements with you in the stack, extra 5 rupee will be in your pocket. You see that the pocket will be having 5 rupees. Okay, now I am asking you to pop out only 3 elements or maximum 5 elements. So whatever the item you are popping out, you have extra, you use that money. So and hence I am not paying anything. And hence I am not paying anything. Okay, so now the logic is clear. So whenever I want to do a push instruction, I have to pay 2 rupees to the system. And whenever I want to do a multi-pop, I am not paying any money. Therefore, if I have n instructions like I1, I2, etc., In, the worst possibilities, because out of these two, worst thing is this one, maximum one is this, right? Because 0, here 2, right? So if all the instructions are pushed, then only we get the worst case. If all the instructions are pushed, 2 rupee here, 2 rupee here, 2 rupees here, so totally 2 in the end, so that is equal to R of n. Now you see with the R of n time, we can complete the task. So this is what amortized analysis. And this can also be done in another way, one more way. So that is called the potential. This is also a standard method. Anyway, some your syllabus not correct, but when you are going for advanced algorithm, so this may be required. Okay, potential method. So you might have seen in the physics, right? Potential energy, kinetic energy, like that, and sometimes potential difference and all you take, right? So let us not go to that. In the potential method, I define the amortized cost A is equal to TA plus pi A minus pi I minus 1. First, let me give the formula, then we can go further. So AA is amortized cost and TA is actual cost, and this is the potential difference. Okay, pi A minus pi I minus 1. This is potential difference. Okay, now if I take this formula, whether this formula is correct or not, that we should confirm, right? So some formula here given, you cannot simply use no. So we have to confirm the formula is correct or not. So here there are n instructions. This is for ith instruction. This formula is for ith instruction. There are n instructions. So we have to add all the cost, right? So sigma I is equal to 1 to n AI. That is equal to sigma I is equal to 1 to n Ti plus sigma I is equal to 1 to n pi I minus pi I minus 1. Okay. So this is the total actual cost, sorry, amortized cost. This is total actual cost, and this is the total potential difference. Now this is equal to sigma I is equal to 1 to n Ti. Now if you add that, some of the terms get cancelled. If you expand it, you will be knowing that. So finally what you have is you will get only pi n minus pi 0. So all the remaining terms get cancelled. Okay. Suppose this potential difference pi n minus pi 0 is positive. If this is positive, then if you remove this term, what happens? Suppose this is positive, what happens is, okay, this sigma A amortized cost will be greater than equal to the actual cost. If this provided this is positive, provided this is positive. So now whatever amortized cost you are obtaining through this formula will be an upper bound compared to the actual cost. So how we get the positive? This is a user, this pi is a potential function. This pi is called the potential function. So this potential function is a user defined one. We have to define. This varies from problem to problem. And again, amortized analysis once again not easy for all problems. Not all problems having amortized analysis. Okay. So if you are not defining the potential function properly, you won't get the answer. Okay. So this is a user defined point. So user can define the potential function such a way that if pi of n is pi n is greater than pi 0. If pi n is greater than pi 0 means the difference is positive. Then the amortized cost what you obtained here will be the upper bound. Upper bound. Okay. Now we can come to our problem. First, here the task is, I think okay, 3 minutes I can finish up. Okay. We have to define the potential function pi a. What is this pi a? Pi a is number of elements in the stack after ith instruction. Pi a is number of elements in the stack after ith instruction. So that means we are doing instructions are push or multi-pop. So we are pushing some element or popping out some elements. Okay. After that, how many elements in the stack? So that is what the pi a. So in this case, when you say that, then what is pi n? That is after your instructions number of elements, and pi 0 is without doing any instructions, right? So without doing any instructions, pi 0, I mean equal to 0, right? The thing is the stack is empty. But after an instruction, maybe some push, some multi-pop, it cannot go beyond 0, right? So we can say that pi n is always greater than equal to pi 0. And against the condition hold good. If you take the potential function is like this. Okay, now what is our instruction? First we can take push instruction. If ith instruction is push instruction, K is equal to TA. TA is the actual cost. What is the actual cost for pushing one element? Only 1 unit. So TA is equal to 1, right? Then pi n, our formula is A is equal to TA plus pi I minus pi I minus 1. So actual cost is 1. Then pi a. Ith instruction is push instruction. We do not know how many elements already. So let us assume let pi I minus 1 is equal to alpha. So there are alpha number of elements in the stack. Then pi a is equal to alpha plus 1 because ith instruction is push. One more element added. So that will be alpha plus 1. So it is 1 plus alpha plus 1 minus alpha. So that is equal to 2, right? So this is what the 2 rupees we consider in the accounting method. This is what the 2 rupees we consider the accounting method. Okay. Then another instruction is multi-pop. So multi-pop, there are 2 cases. First case is number of elements we try to remove is less than or equal less than number of elements inside the stack. If that's the case, if pi a minus 1 is let pi a minus 1 is equal to alpha means pi a is equal to alpha minus k because all the k elements can be removed. Then your amortized cost A is equal to actual cost. Actual cost means we are exactly removing k elements. We are exactly removing k elements. So actual value is k, then plus pi I. Pi I is alpha minus k minus pi a minus 1 alpha. So alpha alpha goes, k goes, that is equal to 0. So this is what the 0 rupee we consider in the accounting method. Okay, next case. Next case is k is greater than or equal to cardinality. That is, in this case, all the elements available in the stack that will be removed, right? So what is amortized cost? A is equal to actual cost. Actual cost means all the elements will be removed, right? Because k is larger. So actual cost is cardinality of S plus pi a. Pi a means number of elements after executing ith instruction. Now what happens after removing all the elements? 0 elements are there, right? And pi a minus 1, that is number of elements already there in the stack. So once again, cardinality of S minus cardinality of S, that is equal to 0. Now you see once again we are getting 0 rupee as we consider the accounting method. Okay, now if this is 2 and this is 0, the larger one is this, that is a push instruction. And against the worst possibility is if all instructions are pushed, and if that's the case, like in the accounting method, it will take 2, 2, 2 like that. So that is 2 into n, that is equal to r of n. Okay, now you see the normal worst case, it has given order of n square time, but when you look at the amortized analysis, we are getting a better upper bound. So that is order of n. Okay.